What's up? What's up? I've been working on a periodic table of currents, so I wanted to just kind of go through it. I've made some progress since my last video. So, the general principle is that there is a current that flows into a channel inside of a polygonal shape that contains the current, and then it does things. So in the first instance, it just goes in and out and creates a eddy, which is then a space for the current to flow, which is effectively a positive charge, the space. Whereas if the space is filled, this current comes and brings in mass that accumulates into a new steady state where it essentially becomes a mass. Then essentially now we have a neutron, and again the eddy exists, and it essentially spreads out the polygon, moving material, creating just a higher density wall of the polygon to a sufficient degree to support it. But then a second neutron comes in, and at that point, this eddy and the inlet are in line because of the neutron just taking a position over here. So the eddy then is more in line with this current. So it just essentially cuts across and cuts through the initially single channeled polygon to then enter into helium. So then we cut across from hydrogen, not necessarily with two protons. It could also have a single proton and become helium-3. But helium-4 perhaps, this pathing. So I'm just going through it. This is the general concept. So a physical channel is carved through a polygon, which then builds a mass by its current flowing through the polygon, and then it cuts channels, and then each time that it goes helium to, now we have two channels, but the flow is still going in a single direction. And then lithium, again, it is splits one of the neutrons and carves another channel. So from this progression, we arrive at first just like a triple vortex, triple eddies with triple mounds, but that just tends to push a mound over here, which then leads to lithium 7 versus 6 without the fourth neutron. And then I kind of did this. At this point, I started drawing this way, and I was like, well, this is kind of weird because it would bring the flows back. And I kind of paused, and then I started to, last night, I had this thought, what if? Like, well, how can I simplify this drawing, first of all? And so I started doing this, where there's just a current coming into a polygon. So I draw neutrons on this as just single dots. The current is just a line going from left to right. So because it goes left to right, wraps around it, and right to left, it basically is the same inlet and outlet shared. But no mounds. And then there's also the polygon around it that I just didn't draw, which is just assumed, like it's just around it. All these have a polygon boundary holding this shape to be. So in this case, there is no neutron, but then it creates a mound. So now there's a neutron, and then two neutrons. Still the current's going back. Then it cuts through helium-3. It cuts through, has a neutron, and then the two neutrons cutting through. Also with some subtleties here for eddies. So at this point, I'm not putting any protons in. That's the thing with this, is I'm not putting protons in yet. I'm basically just building the arena through which the current flows, where the eddies are formed. So they're just like dependent on the current flow in the instance of the shaping of the atom. Like if it had enough current, it would produce another eddy, which would then produce another space for current to flow, which would then produce another proton. Whereas a neutron is when the space becomes filled by an actual mound of material because the current is physically causing a mound of material. So last night I went through hydrogen where it just comes in and out of that polygon, produces two mounds. Then it starts to carve through, so then the path just goes left to right, one neutron, two neutrons. Then it divides one of the neutrons. This neutron divides into splits, and then the currents rebuild and establish the mounds so that they are basically neutrons equivalents, where there's similar masses across the neutrons. And then this structure is lithium-6, but then it essentially has a potential back here, which is drawing off of this, where essentially it fills in behind. And so my thought is, once it fills in here, the current coming to the bottom half of this is not able to come through as easily, so it's more tends to go this way. So the next neutron to be split is the one over here. So I believe the current comes over and splits it just the same like this to produce like a forking structure, because the current's generally going this way, so it's essentially doing that. That's the thought. So then we run into lithium-7, where that's happening, and then again it splits this one to become 8 plus another eddy to become 9, so another eddy, 3 to 4 beryllium plus another neutron from the splitting, 9. And so we're going to notice that there's certain structures as we go that tend to like stabilize around, which strong isotopes included, the stable isotopes, which strongly suggest that there's something of this current nature, where there is a current going through, shaping mounds, producing different elements, that there is such a thing going on. And so again, it produces another mound to kind of stabilize both sides, and then another eddy. And then the structure repeats with just another eddy. So that's the thing. When a structure is stable, like this structure, it repeats. If it's not stable, it needs another mound. So like here, it's not that stable, so it added another mound. It only did, or I guess it is, yeah, it only did 2 of them here. It didn't do like, although, yeah, nitrogen doesn't have one. At nitrogen 13, maybe like considered radioactive, like it'll decay. So it fills in this space next, and then it just immediately, because this is unstable, it needs another supporting mound to like fill in. So it divides, producing another mound here. And just fills in the structure. But this structure itself is stable enough to support another eddy, so nitrogen can actually have the same arrangement. But then also this structure is really stable, even though this carbon is unstable. So essentially it's so stable that it almost needs another eddy in there. So it's not stable with only 6 eddies, but it becomes stable with 7 eddies and with 8 eddies. So it repeats again. It's just not, it's too much mass and not enough like space for the current to flow. So it kind of pushes outward and spreads out the carbon-14, which decays, I believe, into nitrogen 14. So essentially one of the neutrons becomes an eddy. It's just not stable enough. But if it stays this way and a new eddy is formed, then it's just nitrogen. And then again, a new eddy is formed within this stable structure able to contain these like eddies within it. Then it repeats again. And then oxygen has two additional isotopes, which makes sense that it wouldn't just have one if it's adding off the ends like this, where this would kind of make sense as a final like isotope that's stable. And then it repeats again with fluorine. So like this, fluorine doesn't have this one because it has too many eddies, which would essentially bring it back to like nitrogen's 15 maybe. Like pop one of these off. Whereas oxygen 18 and fluorine have the same structure, and again it repeats. Again, it's because of its stability at the back here. It's like balanced across the whole structure. Because of that, it's able to include additional eddies within it. So another proton forms, so just more eddies. And then at that point, as the current increases, like it can't have 9 eddies and then have like more structure to its neutrons. It has to sequence up from oxygen to more eddies to then begin to have enough like outward pressure and inward pressure to accumulate these masses around its boundaries, which then leads to 2 additional isotopes within neon as it like sequences up to a new steady state. And so again, the structure at neon's stable like structure here, it repeats again. The only stable isotope in sodium repeats again in magnesium. So we're seeing like stable structures of the dot arrangements based on the current flows that are producing stable, like repeating structures of the neutron arrangement, which then allows for additional eddies, just another eddy. And then at that point, it needs another mass around the boundary. So it adds that, but then it's not balanced, so it needs another mass, so it does that. And then suddenly it needs another eddy, so it repeats the neutron structure, which is stable. It repeats it again because it's stable, and just adds 2 eddies again. And then again, we run into this issue where it adds 2, not just a single one, but a double to balance out the end here, to essentially lead to this structure with 16 neutrons arranged, and then just 14 eddies within it. And again, it does the same thing where it's nice and stable, and so it allows for the insertion of more eddies. Here's another eddy. And then I realized this is where I made a mistake. I moved on from here to go to chlorine and so on like this. And I think I made a mistake because I started to look through sulfur. So that's where I was. That's why I was making this video. I was kind of catching up. So here we are coming in with this structure, repeating structure. Okay, so let's just start drawing it. I'll just draw it. I won't even look at my notes unless I feel a little confused for some reason, but it seems followable enough where I can just redraw it without like. So it seems, my thoughts are, in some reason, it tends to, because the current's going left to right here, it tends to add on like this. And then like this, just the same. So I'm just going to draw this without the dots and just assume the dots, because I do think it's possible to just like know. that there are dots this whole way, and then elevated dots this whole way, and elevated dots this way. Basically, this elevates the dots and elevates the dots to the sides. So then we have a new structure like that, but then again, it's the same thing where it basically, it would look like this if I had finished it. And so it would have this stable end, but then sulfur, it doesn't, I guess it just isn't stable enough with just another particle there, so it does two of them like this to finish this like backbone again. So it really keeps forming backbones according to the isotopes. I'm going by the isotopes in part. And so chlorine as almost like a handrail to guide me through. Okay, so we notice chlorine it's just another eddy within the stable structure of what occurred in the sulfur 34, where it has openings at the end, but then it's again the same stable. Both of these structures are stable, so both of them can exist with additional eddies added within them. So chlorine and sulfur both have the same structure, but again, argon, that's why I think it does it this way, because this structure makes sense and it repeats here around these specific isotopes. So argon, again, same structure here and same structure here, where it's just filling in the end. Okay. Now again, now we notice potassium does not have this structure. So this structure, even though it repeated 3 times, or 4 times? No, 3 times. Did I add? I might have added something here. This. Just draw over top it. What do you mean? There we go. There we go. Yeah. Okay. So this structure repeats 3 times, but it doesn't repeat again. This structure stabilizes, repeats here, repeats here, repeats here, and then we just see again another eddy is stably within this backbone structure, able to form. Without changing it. So 1, 2, 3, 4 times that backbone structure appears, which is really makes sense if it is like a backbone structure like that, in which eddies can form of different amounts, causing different amounts of spaces within it to then lead to different properties of the structure. I don't know how the subtle differences lead to the like immense changes in the properties, but so if we just continue on with this and just assume maybe then it kind of tends towards more of a backbone structure, and maybe it wraps around. I believe that's what I did. Yeah. And then this. So again, it's just going through the 2 isotopes to stabilize the tail of it. in essence. Okay, now we're up to calcium 2040, and check this out. This structure so stable it repeats again. Cool. And then the same thing happens, or it just adds. And then adds. 1, 2, 3, 4, 5. Now we're kind of hitting that point where I started right. Yeah. Let's look at this. This one decays into potassium 41. So essentially, it's like one of these spaces, like this space here, just kind of has its material removed. Pardon. And then that basically makes it that region that the polygon had a space in, and a space for current to flow, which is what a proton essentially is within the structure, is the amount of places where eddies were able to form and produce like some unit that just is what we call a proton at that point. Where the shell of the like body of this polygon and its upper and lower layers maybe are like the mass of the proton, because it has mass, but it carries the current, which is the space, the opening where the eddies form. But then the neutrons have those openings filled with the electron's mass, which is what's the current flowing through it is just in place, and it's held in place by some sort of locking mechanism that is essentially like an anti-neutrino. So it can sometimes come out, emit particles, and essentially become decayed. So let's see if that makes sense in terms of isotope calcium decay product. (41). Where is it? There it is. Decay mode, electron capture, proton rich nucleus. Oh, I said that backwards. Where essentially the proton space becomes filled by a current that pushes a mound up to be like this one, essentially this structure, right? That's what that one is. Yeah, to be the more stable structure. It just makes that unstable, destabilized, imbalanced end become a stable structure. That's again repeating. So we can see 22. If there's any 22s anywhere, we already did that one. At this point, we're running into 23. This one needs an additional one, needs additional 24. So I wrote ahead because 24 is the only one. This one stabilizes at 24. where this one is 20. So maybe we can just, these are just increasing backbones. If we say this goes like this and goes so then it has, wait, have I been drawing too many? Oh, did I add too many lines? Maybe. I think that this should be just 24. But there's been 2 behind it all along. It's 18, let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Not this. Oh. Not this. Scheiße. Okay. Let's undo those strokes there. Just do the same thing I did before. Some reason when I don't know what I'm doing that much when I erase. It like produces a background color. I think that. This one's right. I don't know. Right? No, it's not. No, it's not. No, I was hoping it was. Tiniest pen. Alright, fine, I'll make it 20. That should help. I just don't want to make it all. Okay, 1, 2, 3, 4. I really messed up. Okay. I mean, I'll just take the ends off and fix them. This one is just straight up like that. Okay. No. Probably this. Okay. Let's just make sure then. One of the benefits of those dots for sure is following what I'm doing. Okay, this one added 2. Now it's 20. 1, 2, 3, 4, 5, 6, 12, 22. Wait, is this right? 5, 10, 18. So how did I? Oh Lord. Pardon me. Please be right. I was like, I can figure this out on camera. Like, I kind of got this part done, but I just literally just miswrote this stuff. Okay. I think we're catching up. That should be 10, 20. Okay, that's better. And then this one needs to be 18, which is the same as that one. Okay. This one needs to be 20. So that's the same as that one. $18, same as that one. Okay, we're looking good. That one down bottom's probably wrong. 20, that one needs removed here. Darn. Okay. Oh my god. The ripple effects. I hope if you're watching, you fast forwarded. Okay. Okay, let's add this here back. This one should be there because it's out of balance. So there for sure. This one's good. Good. Okay, now we're good. Now we're good. Back there. That's good. That's good. 1, 2, 3, 4, and a fifth one. That's good. 1, 2, 3, 4, 5. So this one needs 24. So I definitely need to remove this also. Whatever. Okay. One, 2, 3, 4, 5 on 21, so 26, 27, 28. This should add to 45. 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. Alright. Okay. The reason I really wanted to do this was because it's like a hinge again. So that one is 24. Let's see, does titanium do 24? It does exactly the same. So that's just, that kind of reestablishes that it probably is like that. 1, 2, 3, 4. Perfect. Flawless drawing, I know. You can marvel at your leisure. Okay, so this one is not the most stable. Let's look at it. Isotopes of I realized I can just do that. Okay. Really, 50 is barely any. Barely any. But it's pretty stable, like relatively. 10 to the 17 years. That's pretty stable. So I put it because of its like duration. But it notably decays by adding a proton. One of the neutrons kind of blows out and becomes a space for another eddy, I guess. Because it remains 50. Okay, so that gives us some indication, though, that there's 28 here. So if there were 20, if there were 24 here, 28 here, we would just again add another 4 to the same backbone. 1, 2, 3, 4, and 5. That adds another 4 because this is 6, 8, 8, 6. We need what? 28, 16, 22, 28. So that makes sense for it being stable. Maybe it does something like this. That's depending on what's 26. So this one has 26, which is probably just without like this back row having 4. Instead, it's just got 2. So the 26 structure, but for some reason vanadium doesn't. It's not good with just 26. Like it needs at least another neutron. So really, with only 26, it just immediately has another eddy. For some reason, like it can't stably have too few eddies with 26. Although it does here. So it's kind of odd that vanadium wouldn't have a 26. Like a 29, 49, or a vanadium 49. It's odd that wouldn't have like a lot of stability based on this. So we got 1, 2, 3, 4, 5, 6, 7. So just one more like this and like this. Just like an outlet kind of thing, I guess. But I think at that point it has 1, 2, 3, 4, 5, 6. 16, and then 6 and 6. One of these is not there at the back, is why. Okay. Now let's kind of flow inward. 27 to 26 would probably just not have this one. So titanium we can probably draw straight across with 6 rows of 4 and a leading row of 2. Leading row of 2 plus 6 rows of 4 here. Maybe I'll draw it like that. It's like an antenna. No wonder it's conductive. If it's conductive, it's conductive, right? Of course it's conductive. What am I talking about? What am I talking about? I don't know if that actually makes it conductive, but it looks kind of like antenna-like. This is also, that's why I put this little notch here. This is the most stable one, which kind of makes sense. Where if we just did it without one of these here, so maybe I'll just go like that, 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 like that. Where it has a dot here and a dot here, but not here. And then This looks like these ones fill in the end. So if we come out, that's the 6, 6, and then 2 at the end. And then just not doing this, the 2 at the end, only 1 at the end. 1, 2, 3. So just 1 at the end there. Fill it in, fill it in, fill it in, fill it in. I'm just like kind of formulating these without any idea where it might go. Like why these structures might matter. Just based on the isotopes. So we made it through vanadium plausibly. Let's keep going. Let's keep going. Oh. Let's just say new. Another 3001. Okay. After vanadium. Okay, we got chromium. Which has 4 stable isotopes, 50, 52, 53, 54, with 52 most abundant. So 50, 52, 53, 54, okay. So chromium. Which is 24, 50, 52, 53, 54. 55. Oh my. 51, 52. Okay, so we're coming from over here. Titanium 26, this structure. So let's just say 26 goes out this way, straight across, cuts across here, and then just kind of fans out like this. Two, 6, 10, 14, 18, 22, 26. And then again, it skips. It's like we don't really want 27, so it goes straight to that more stable backbone, where the end actually rejoins and has 2 there as well. One, 2, 3, 4, 5. So I need to make sure I have 5 lines here. Okay. Then that's 28 neutrons. And just within all of this is eddies. Probably again, based on the fact that there's 53, 54 here, not 55, that it just fills in the end here and does this one here and this one here and just adds another. Somehow this like rearranges in 3 dimensions to make more sense. I know it's kind of just becoming a line. A long extended column. So now down here comes across. to the point where we also have these coming out. Okay. So this comes up. That's that one, or that's this one. So then 1, 2, 3, 4, 5 more. And then I actually just drew the structure for that one. So I need 6 lines here. 1, 2, 3, 4, 5, 6. And then I just need to erase this little bit here. Okay. Just fill in the dots on the end as the outer boundary of dots. Maybe that's a good approach. Just build the outer boundary. Okay. So that seems to make some sense. Manganese. It's MN, right? Yeah. Like, I ain't no MG up in there. Isotopes of manganese. Okay, so one stable isotope 55. 55. 55. Only stable isotopes add a proton. Maintain this structure. It's kind of odd, honestly. Again, this is anomalous that this structure here is not stable for manganese. It may lead to the realization that I'm starting to deviate from how these actually assemble. Like, they may start to assemble further outward at some point. Because essentially, this would just be a repeat of that. The only stable one. Let's get to iron. Let's get to iron. We're at iron. Maybe that clears some things up. Iron. Stable isotopes of iron. Okay, we got 54, 56, 57, 58. Let's look at that a little bit. Okay, stable. Years, couple years, 60s. Pretty relevant in terms of its stability, but it's also trace amounts, but we can note it. It's also high up in the sequence of neutrons, where it's likely where more eddies will be forming at that point, so that it just becomes cobalt instead. Okay, so what was its isotopes are 54, 56, 57, 58. Okay. 54, 56, 57, and 58. Iron. So this one's got 28, so let's just go up here. Manganese wasn't able to stabilize around this structure, but iron is. So the one that comes across and then comes this way, and then 5 times, and then the ends are stable. This kind of looks like an electron configuration, like an actual two ends of an atom. Like if I just ignore the center, the way this is. Well, not that that necessarily would mean anything. Okay. Interestingly, it skips over again 55. It doesn't like this structure. Chromium was able to stabilize in it for some reason, but other molecule or atoms are not able to. At this point, I'm just gonna put repeat of. Same structure as chromium 54. Okay, and then another another two of these. So essentially it's going to do the same thing. Or it does this. And then it does this and fills in the end to stabilize the tail at higher current flow rates when the atom's being formed, probably. So let's just draw the tail and put dot 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 maybe. Okay, so it's gonna have an extending portion there. And then the front end like this. Okay. And again, same thing. Front end and tail end. Dot, dot, dot. Okay, let's go to cobalt. Cobalt. Isotopes of cobalt. Really, it's just stable 59. Does that make sense? That's probably the one where it has the structure at the end. 59. This one, yeah. It's cobalt's 27, 59. Same structure. One, two, three, four. So here there's 4. Here there's, wait. Did I do that right? I think it's like this. With a tail of 1 at the end. Like that. And 4. A 4x4. 4x4. Four by 4. Okay. So that's 16 plus 2 ends of 6 is 22 and 5, 27? No. I need 31. So it must be missing another row. 5. So this must be 5. 4 times 5. I must just not have drawn enough here. Let's see. 2, 6, 10, 14, 18, 22, 26, 28. Okay, that's good. That one's good. This one's 30. Okay. That one. But then we go to... yeah, whatever. It doesn't matter. It just adds another. Okay, I think it's the right number, so I must just be not able to tell when all the dots that I'm freaking putting here. Okay, so cobalt only has that stable form of 59, which makes sense. It makes sense when it has the two ends. And then we come up to nickel. And then we need its isotopes. Oh, the tabs I have. Isotopes of nickel. Okay, 5 stable isotopes. 58. Okay, 58 is the most abundant. 60 is pretty abundant. They're all abundant enough, really. Okay, let's say 58. 58. Nickel. 59. Nickel. Not 59. 60. $61, $62, $64, $61, $28, $62, $28, $64, $28. So we see that same, like it probably builds another layer, another backbone structure. Okay, then because it's 30 neutrons, we can pretty much just say where is that? This one, CR54, CR54, same neutron arrangement, just more eddies. And then 32 protons or neutrons, which is again here Fe58. And then 33 is nowhere to be seen. So now we start running into more neutrons. In order for more eddies to form, this backbone needs more neutrons. So then we run into the same thing. That's it. 1, 2. So it fills in like this. 1, 2, and then again stably adds 2 at the end. 1, 2. Without having an intermediary stable one. So then this one is gonna be straight across 2. Wait, 33? Yeah. And then 4 by 4 or 4 by 5. That's 4 by 6. 4 by 6. 4 wide, like this way. 1, 2, 3, 4 by 6. 1, 2, 3, 4, 5, 6. And then that's 24, 26 plus 28 is 46, 54. So we need 7 more. So even another 4. So 4 by 7 would have been more appropriate. And another 3. 1, 2, 3. And then this one goes right to a 4 by 8. In this region. And then this one, 4 by 8. Filling in the back of the spine, and there we go. We're through nickel. I mean, it seems to be making sense, like in terms of how it's flowing. Now we see this stable structure. This one's probably going to repeat. This one's probably not going to repeat. We might see some of these repeat again. Let's see. What's the next element? Copper. Two isotopes, 63 and 65. Copper, 29, 63. So it should be this one and this one. So those two repeat. Copper, 65, 29. So this one's going to just be nickel, 62. The neutron arrangement of nickel 62 with more eddies. The neutron arrangement of nickel 64 with more eddies. And then that's it for copper. Let's just give a glance at copper. I mean, it has many isotopes. None are really stable enough to matter, I would say. Like, they're just things that aren't stable. Zinc. Five stable, 64, 66, 67, 68, and 70, with 64 most abundant, but only 50%. 66 and 68 also pretty high abundance. Okay, let's just finish this slide on nickel, or zinc. Zinc, 30, 64. So this one's got a 34 neutron arrangement, which is basically this one. Same arrangement again. And then we got, that's the most abundant also. Most abundant is this, the one with this structure. Some reason. 66, zinc, 30. So again, nickel, 64 as the neutron arrangement, just with more eddies within it. 67, zinc, 68. And 70. Okay, so 37 neutrons from this structure. We go back to this structure. 37 and 38. So basically it does the same thing where it adds one here, dupe, adds one here, 30, 38, and then it adds two here. So we have a cross here, dots, two dots, and then a 4 by what's it out in office? That one, 4 by 8. I'm not sure. Is this right? It's 24, 26. Or no, 32. 32. 34. 36. Okay, this line can go. It doesn't actually need to be there. It just makes it as if I'm like, is there one up there? Above it? Okay, that's better. Okay, so it takes that 4 by 8 and adds another neutron. 4 by 8, and then 1, 2, and this one actually is like that. To then be 4 by 9. Just straight up to the end of there, which is, right, 36 plus 2, 38. Yeah, okay. And then plus 2 at the end to then fill out the structure. 4 by 9. Zinc, 30 elements. I would say those 30 elements, maybe ignoring my mistakes and like actual like mistakes in the writing, or I added too many or whatever. Like this makes sense. I was able to actually make sense of the isotopes through 30 elements. Good sign. That's a good sign. Alright then. Hopefully the next one will be sooner or later more ironed out. Alright. Peace.